In this video, I'm going to talk about the concept of total differential. I always like how this sounds because it sounds almost like a movie, right? So there are several movies that start with total. Total Recall, Total Eclipse, Total Drama, Total Control, Total Differential. So let's do it. Let's explain what the total differential is. So what if we have our machine which has several sliders which are the variables as the input, and we want to know what df is when we move all of the sliders at the same time. Okay, so we move dx, dy, dz. Okay, so what happens with df? So of course df is going to be a function of how much we move each of the three sliders. Okay, so df is a differential which is a function of dx, dy, and dz. Okay, for two variable functions, it's very easy to understand what this total differential is, because it's telling us about, it's like how much f changes in each direction. So that's what I'm trying to show this with all of these arrows. Yeah, so the amount that f changes will depend on the direction in which we are moving within the xy plane, right? And therefore I have created this figure. I often find that some students like this figure if they are very visual, other students just get confused. So don't worry, I'm just trying to help to those students that like being visual. What is the total differential? So if this is the xy plane, yeah, then this yellow surface here is just our function f of xy. Okay, and now I select a fixed x and y, which is this point here. But now I change x by an amount dx, and I change y by an amount dy. So this is like changing our two sliders by a certain amount, dx and dy. And then the slider of df changes. So it changes from here to here, right? Because we changed dx and dy, and therefore f changes from here to here, which is this change, which is df. Okay, so this is the total differential of f. Now, what is the total differential of f? Well, if you zoom in enough into any continuous function, then any curve disappears and it becomes a plane, right? This is the tangent plane. So if we look close enough, this is always a plane. And this will happen when dx and dy are differentials. They are in the limit when they go to 0, and therefore this will become a plane. And then finding df is very easy, because you can just find the height of this triangle here, and the height of this triangle here is given by partial of f with respect to x, which is the slope in this direction, times dx. That will give you the height of this triangle, plus the height of this triangle here, which is a right angle triangle, whose height is given by the partial of f with respect to y, which gives you the gradient or the slope of this line, multiplied by the step dy. And this gives you this height here. Okay, and by adding this height to this height, we end up with this height, which is df. Okay, therefore you can write that the total differential df is equal to partial of f with respect to x times dx plus the partial of f with respect to y times dy. Okay, now if you got confused by this figure, don't worry, you just have to remember the equation. And actually, I can write here the general equation when the function is more than two variables. So it's a function of n variables, okay? So then the total differential f df is equal to the partial of f with respect to the first variable, dx, times dx, plus partial differential of f with respect to the second variable, dy, times dy, plus dot 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 until the last variable. Let's call it, why not, z. Partial of f with respect to z times dz. So this is the expression for the total differential of a function. And remember, this is a function of dx, dy up to dz. So the total differential is itself a function. Okay? In the next video, I will do an example where we'll calculate the total differential of some function. See you in the next video.